Right. So we'll talk some more about integer modeling and modeling with integer variables. And we have two models that we'll look at here. One is the quadratic uncapacitated facility location problem, and the second one arises in support vector machines, which is a tool in machine learning. And I copied those or stole those slides from Pietro. So this is a problem that was chosen by a group of mathematicians because it allows strong cutting planes to be derived. The problem here is that you have a number of facilities or a set of facilities, M, and you have a set of customers, N, and the customers can be supplied from different facilities, and the percentage of a customer's demand, customer J's demand that's met by facility I is Xij. And we have binary variables that tell us whether a facility is built. So the goal is to build facilities to meet customers' demand. There's a fixed cost for opening the facility, for building the facility, and then a quadratic cost for meeting the demand. And so this problem can be written down in a compact form. So the first term in the objective is the fixed cost of opening that facility. So Ci is the cost of building the facility, and Zi is the binary variable that tells me whether I open the facility or not. And then there's a quadratic cost, so Qij is a coefficient, and the amount of customer J that's supplied from facility I is Xij, and the cost is quadratic. So it becomes more expensive the more you supply from that facility. If a facility is not opened, then I can't supply any customers. So that's this first constraint here. And every customer wants 100% or all of their demand satisfied. So that's the second constraint here. But notice the Xij are continuous variables. So Xij are the fraction of demand of customer J supplied from facility I. So the customer's demand has to be met from these facilities. And then the customer demand, the fraction that's met is non-negative. The customer isn't sending stuff to the facility, and Zi are the binary variables. So that's a very simple problem, but it has a lot of nice structure that we're going to look at a little bit. And this is also a good point to sort of get you familiarized a little bit with AMPL. So in the afternoon, we have a tutorial on AMPL, the modeling language, and I'll give more examples later on. But what I wanted to write down is a sort of partial model, what this would look like in AMPL. So whenever you see this kind of text font, it's directly taken AMPL models. So there's some variables, Xij, I and J are index sets here. That's previously the M and N that are non-negative and less than or equal to 1 at the first line there. And that's the percentage of customer I served by facility J. And there's a variable Zi that's binary. So the notation here is very similar to what was on the previous slide, right? On the previous slide, I had Xij non-negative and Zi binary variable. And I switched the notation, the index sets a little bit. And then I'm telling I declare an objective function. In this case, I minimize the quadratic cost. And that's the sum of the fixed cost. That's the first sum there. And the second summation is the sum of the variable cost. And you just write Xij squared. So Xij is the variable, and you don't have subscripts because that's sort of not possible. So you write these bracket notation for indexing variables. And it's very similar. Look at this sum I and I. That's very similar to what we had on the previous slide. I had a slightly different one. I had I and M and J and N. So I changed notation on you a little bit, but it has the same flavor, this AMPL model. Then there's this variable upper bound constraint. So you introduce these constraints. And whenever you have these parentheses, brackets, that means for all. So think of what's in here. That's a variable upper bound that holds for all I and J and J. You have this constraint. And then there's a constraint that you have to meet the demand of every customer by summing over the facilities The fraction of the demand has to be equal to 1. So this looks very similar to what you're familiar from a math notation, which is really nice. That's what we like about modeling languages. And in fact, it's an incomplete description because I haven't told you what I, capital J, Q, and C are. So that also has to go into the model somewhere. But it's very intuitive to write these AMPL models. You declare some variables, you define what the objective function is. You have this little sentence that says subject to. So those are going to be your constraints. You give the constraints a name. So having named constraints is nice because you can refer to them later on. And we'll do all this in the afternoon. And there's lots of examples that we'll look at. It's very intuitive. The nice thing about modeling languages is I can just write this down, and I have lots of solvers that can now tackle this problem. I'm not just limited to one solver. I don't need to provide gradients. So if you're like me and not quite sure how to differentiate xij squared, then AMPL will do that for you and will provide gradients in a very efficient way. So here's a little bit of this Linderoth theorem that said that we use these binary variables as indicator variables. So what we observe is that if zi is equal to 0, then xij is 0. And if z is equal to 1, then we need to model the epigraph of our nonlinear function. And we're now going to do this in a sort of trying to build on getting really tight formulations. And our goal here is to do indicator variables and introduce indicator variables in a way that allows us to get good, efficient relaxations. So on the left here is an example of an integer linear feasible set. The integer points or the integer lattice are the red points. The blue lines are linear constraints, and the blue region would be a feasible set of a linear relaxation of the integer program. And then we talked yesterday about the convex hull. The convex hull is given in green. So our goal when we're making these formulations is to get similar formulations to these where we get convex hulls. But this is going to be slightly harder because we're going to have to do this over these nonlinear functions. So we're going to try to mimic what we're doing in mixed integer linear optimization in this nonlinear world so that we get good relaxations. Okay, so here's how we can do this. In particular, we're going to study sets of this form R, where we have z is a binary variable that's indicated by the b there. So the notation b stands for binary variable. We have two continuous variables, x and y. And the set that we're studying is this very simple set, which is the quadratic cost y, which is x squared, and the variable upper bound constraint on x with an upper bound that in our case would be 1 on the demand that is supplied from the facilities, z, that's indicated by z. So we're abstracting what we had with indices now to a very simple set. And what this set looks like is actually the following. So if z is equal to 0, then we can just look at this, then x has to be equal to 0. That comes from the second constraint. And y is non-negative. That's the first constraint. So this set is the union of these two green sets. If z is equal to 1, then x is less than or equal to u. There's some upper bound here that I haven't drawn. And y has to lie above the green line. So y is greater than or equal to x squared. So the set that we want to model is actually the union of these two sets. And if we can model this in a tight way that corresponds to the convex hull of these two sets that I've drawn there, then we have a good chance of solving these problems efficiently because the relaxation will be much stronger. So that's what we're going to do here. And the convex hull is in fact given by taking lines that are connecting the origin to points on this curve. So I take different points on this curve and I connect to these. So that's what you see here now would be the convex hull would be this set here, and then the lines connecting these, and the epigraph of that would be the convex hull in the Z plane. So this is a sort of fundamental theorem that says that you can actually write down analytically what this convex hull looks like. And the convex hull indicated by the convex hull of R is given by the second line. So we can sort of look at this a little bit. What we have is we have, instead of binary variables, now all the variables are real. So we need to add the upper bounds on Z back in at the back. Y non-negative is a constraint that we had earlier. Well, and we have the variable upper bound constraint on X. And now we have this funny looking bilinear term, YZ is greater or equal to X squared. So this looks like we've made one of the mistakes by multiplying sort of bilinear functions and linear functions. But in this case, that's okay because it's actually a binary variable. And so what this set is, in fact, is a cone. And so you can show that this constraint here, that's sort of central in the set, the nonlinear constraint for Y, E, and Z non-negative is a cone. So it's a conic constraint. And that's beautiful because this is a convex set. And in fact, it's a second order cone, and there exist good algorithms for optimizing over the convex hull of R. So what have I done, or what did we do? We started off with the definition of the mixed integer set, and we wrote down the convex hull, and then realized that this convex hull is in fact a second order cone, and there are efficient interior point solvers for solving optimization problems over convex cones. So I can now solve problems over the convex hull. And so now the hope is that, similar to the linear part, when I solve for the convex hull of the linear integer set, I get an integer solution. The hope is that I get something similar. So this goes back to this picture that I had here. If we minimize just over the original set, then the solution might not be an integer, might not be a red point. But if we minimize a linear function over this green set, which is the convex hull of the integer feasible points, then we're guaranteed to find an integer solution. And so we have the same or a similar thing here now, except we now have a nonlinear set. That's the convex hull of our original feasible set that we constructed. And so this is a general principle that we really would like to do. If we would like to take constraints that arise in a general way, abstract them to very simple sets so we can study them and find the convex hull of these simpler sets. And if we can do that and find solvers for efficiently solving these problems, then we have a good way of solving mixed integer nonlinear optimization problems. And there's this really nice result that these cones are in a lot of problems. And I didn't believe that until I looked at it myself. So Miles Lubin and others looked at a lot of problems that are in an optimization library, MinLP-lib2, and they showed that most of these problems can be represented by just 4 different cones. So even though there are a lot of nonlinear functions out there, there's an infinite number of nonlinear functions that you can compose, a lot of problems are conic problems. And so there's quadratic cones, there's these rotated quadratic cones. That's the one that I showed you a moment ago, where we had y times z greater or equal to x squared. That was our version of this cone, but it generalizes to higher dimensions. And there's power cones and exponential cones. And these cones all share the same property. Those are all convex sets. So that means I have a lot of problems that, and if I can solve optimization problems over cones, then I'm in really good shape. So these convex cones give very strong relaxations, and you can actually build on something called disciplined convex modeling, where you build up convex models from the start. And so you have nonlinear functions, but you know you have a guarantee that these functions are convex because you're constructing them in a certain way. There's one slight disadvantage, and you need interior point solvers, and they don't warm start very well. So it's difficult if your relaxation doesn't give you an integer point, then it's difficult or more expensive to warm start then. But you can use cutting planes, and we've also developed some active set methods for second order cone problems, but that's sort of beyond the scope of this talk here. So what people do most of the time is then use cutting planes and use these formulations to derive strong cuts. So in the second part, I want to talk a little bit about a model that I got from Pietro, which is a support vector machine. So you probably all know about machine learning and AI. So who's heard of support vector machines before? Okay, who has ever used or been used by a support vector machine? Okay, who has a credit card? Anybody has a credit card? Does everybody have a credit card? Okay, if you have a credit card, your credit card company does this. So they have a support vector machine to decide whether your expenses are legitimate or not. So a support vector machine is a tool for classification. And I fell foul of this once because I did exactly what a fraudulent person would do. We were staying with friends away from home. I did a small purchase for under $50, and then I went to buy something really big. And the credit card company flagged that as being suspicious, and they do that by using these tricks. Okay, so here's what a support vector machine does. You have what are called feature vectors that are in RD and labels that are -1 or 1. So -1 is fraudulent, 1 is okay. Think of those two labels. And XI are the features. So those could be things like, where was the purchase made? How much was the purchase for? What was the delay between making purchases? And other such questions. And so this could be a long feature vector. And what you're trying to do is you're trying to find a hyperplane that separates these two populations. So you have a green population, which is the purchases that are okay, and a blue population, which is the purchases which are not okay. And what you're trying to do is find this red line, this hyperplane, which is given by W transpose X minus B, and you want to have this margin as big as possible. That's what we're going to do. And you also don't want to have misclassified points. So ideally, you don't want to have any blue points in the green ones or the other way around, but you can't usually avoid that. So typically, there will be some misclassification. Do you know what the support vectors are in this picture? Anybody? There's 3 support vectors here, and those are these 3 guys. And they're called support vectors because they support the maximum margin of your separating hyperplane. So you have 3 of these vectors, and that's the minimum number of vectors that you need in 2 dimensions, I think, to get this to have a unique solution. Okay, so what we want to do is we want to find this hyperplane so that when yi is equal to 1, we want the value, if we plug x in here, we want this greater or equal to 1. If y is -1, then we want it less or equal to -1. So we want to do it the right, correct classification. And you can write down an optimization model, and there are 3 models that we'll look at here that we can write down. So there's the first term, you minimize the squared norm, 2 norm of W. You don't want W to be too large in magnitude. The reason is that you want a robust classification in some sense. The second term counts how many times you're misclassifying something or by how much you're misclassifying what you're doing. So the second objective term sort of makes sense when you look at the constraints. So if for all I, we want, so ideally what we would like to have for all I, we want yi times the support vector to be greater or equal to 1, right? If it's a negative classification, if y is -1, then we want it less than or equal to -1. So you get that by multiplying through by yi. And if yi is equal to 1, then you would get the correct classification here. But you don't always get that, and so there's this misclassification error and potentially the number of points that you misclassify. And there's three ways of writing this. There's the mixed integer linear optimization way, where you have a big M variable, and so you're counting how many times you're misclassifying something. There's an indicator variable 1, which says that if zi is equal to 0, then you want this constraint to hold. So that's the indicator constraint that we had in the last lecture. And there's the mixed integer nonlinear optimization way, which now multiplies the constraint by 1 minus zi and makes to ensure it's greater or equal to 0. So that means if zi is equal to 0, then you would have that the left-hand side is greater or equal to it would just come out greater or equal to 0. And you have a minus 1 here, so that goes on. That's the plus 1, so that's the constraint that you want. If zi is equal to 1, then you're kind of ignoring this constraint and you're allowing yourself to misclassify in one of the vectors. Okay, so we're going to look at these formulations a little bit and to understand what they're like. And so the min-low formulation in particular, we can write this down now in its full form. And so we can reformulate this and sort of use the trick or some of the tricks that we used earlier by introducing a slack variable that takes on the left-hand, sort of what's in the parentheses there, the linear term inside those parentheses. So this is a linear expression. Then we end up with one bilinear expression and a non-negativity. And we can now use the tricks that we had earlier to linearize Si times Zi. So Si, if we have bounds on Si, which we can obtain by finding bounds on this expression here, if we have bounds on this expression, then we can linearize our expression Si times Zi. And we can use that to write down potentially tight relaxations. Okay, so this is sort of a general trick that we can use if we want to model this implication. We have some linear expression and we have the implication y is equal to 1 implies a linear expression. Then the model of this would be to introduce a slack variable for the linear expression and have a bilinear equation that says t times and a bound on t. And so if you put all this back together, what does this do? T is then s times y, so y is my binary variable, and I want this to be greater or equal to 0, so if y is equal to 1, then A transpose x minus b will be greater or equal to 0, and if y is equal to 0, then t is greater or equal to 0 trivially, and I don't worry about this constraint. I don't worry what s is. And what I need for this, in order for this to make this work, I need bounds on this linear expression to formulate linear relaxation. So again, I sort of do this trick of creating a bilinear equation, but making it a small number of bilinear expressions, and then creating bounds to use a linear relaxation and do a new formulation. Okay, so this is a very general modeling trick that we can use, and it sort of violates one of the rules that I said earlier, never to multiply a nonlinear function by a binary variable. But here we can do that because we have this nice expansion in terms of linear terms. So the fact that this is a linear expression helps us there. Okay, and so with that, the takeaway points is there's some nice formulations out there that allow us to use, for example, conic formulations, give very tight relaxations, and allow us to do strong cutting planes that we'll talk about later. And I talked about support vector machines and how you can reformulate these support vector machines in different ways to, again, get tight relaxations out of that. So with that, let's see if there's any questions. I should have asked earlier. Yeah. Correct, yes. That's, in a sense, that's a nonlinearity, yes, you're right. And so this holds, right? If y is equal to 1, t is equal to s, t is greater or equal to 0, s is greater or equal to 0, this is greater or equal to 0. Right? And if y is equal to 0, we don't care. And if y is equal to 0, then y times 0 times s is t is 0, and then s can be anything. It can be negative, positive, we don't care.